I'm Lee Teschler, Executive Editor of Design World magazine. With energy efficiency becoming a hot topic in a lot of power handling applications, the topic of measuring losses has become particularly important. That's certainly true for power semiconductors, such as silicon carbide FETs or IGBTs. Power semiconductors experience most of their losses during the time they transition from fully off to fully on and vice versa. To understand why, let's take a look at a typical plot of the voltage and current across an IGBT as it switches on. At the beginning of its turn-on time, the IGBT gets a gate drive voltage that starts to rise at a rate determined by the value of the gate input capacitance. It eventually reaches a gate threshold voltage, at which point the collector current starts to rise from 0 to maximum. While a collector current is rising to its maximum value, the IGBT is working in its active region, which means it's also dissipating power. Eventually, the collector current does reach its full load current level, usually on the order of a few tenths of a microsecond, at which point the IGBT is fully on, and only a small voltage appears across it, given by the collector emitter voltage. The turn-off process is basically a reverse of the turn-on process. The collector current falls in two stages, first rapidly as the electron current supplied to the device stops, then at a slower rate as what's called the tail current, which comes from minority carriers, leave the device. Again, there's a brief time during turn-off when the IGBT is operating in its active region, and that's when it's dissipating most of the power. In practice, you typically measure turn-on losses from the point where the collector current begins to rise to the point where the collector emitter voltage falls to 0. The power dissipated is given by the emitter collector voltage times the collector current. The energy loss during this interval is calculated by finding the area bound by the emitter collector voltage and the collector current during the turn-on and turn-off time. Of course, that area under the curve is given mathematically by an integral. Fortunately, you don't have to calculate it or estimate it if you're using a modern oscilloscope, because a lot of the modern oscilloscopes have special software packages that facilitate calculations like this. One example is the HDO 4000 scope from LaCroix. There's a software package for that scope that will make loss measurements and automatically identify pertinent zones using color-specific overlays to mark conducting and off-state regions. It can measure losses associated with the switching, conduction, and off-state and display them along with a sum of selected loss types if you want. And of course, there's a laundry list of other measurements associated with power circuits that scopes like that one can make as well. Now, for more videos on power electronics, go to powerelectronictips.com and designworldonline.com.